Hello everyone, myself Shantanu Chaudhary. In today's lecture, we will be discussing about flywheels and gyroscope. So, in the last few lectures, we have discussed about balancing of rotating and reciprocating masses, and we have also discussed about the dynamics of slider crank mechanism. So, we will discuss about flywheels today, and then we will move on to gyroscopes. So, flywheels. So what happens? What is a flywheel, and why do we need to use a flywheel? So this is the first question that we are going to address today in this lecture. So firstly, let's say we have a engine. Let's say we have an engine mechanism or a slider crank mechanism like this. A slider crank mechanism like this. So because of the gas pressure, or let's say even if we do not consider it as an engine, let's say if we consider some rotating motor or something. So in a rotating motor also there will be a shaft which will be rotating. There will be a shaft which will be rotating about some certain axis. Let's say this is the rotating shaft in some induction motor or some compressor or something. So generally in engines we also use flywheels. So what is the requirement of the usage of a flywheel? We will discuss now. So let's say this is an engine mechanism. For the time being, we will consider a engine mechanism. So because of the gas pressure over here, this gas pressure does not act always in the mechanism in an engine. Okay, so in an engine there are basically two stroke engines and four stroke engines. So in both of the types, the gas pressure produces the power. So the power stroke happens at any one of the strokes only. So let's say if we consider a four stroke engine, so we will have something called as the turning moment diagram. So T is a function of theta. So this is the torque which this crank shaft will be experiencing, or the crank will be experiencing. So how much torque this crank experiences, this we have discussed in the earlier lecture on dynamics of slider crank mechanism. Like let's say if we have some pressure over here, how much torque this crank will be experiencing. This we have discussed earlier in dynamics of slider crank mechanism lecture. So now let's consider that if we draw the turning moment diagram for a 4-stroke engine, so the power stroke will be acting only at a single stroke. So initially, for the initial two strokes, there will be some suction, then there will be compression, then there will be some power stroke. So and then there will be some exhaust stroke. So this is our power stroke. So this is the power stroke. Here the compression, here the suction takes place. Where the suction takes place, there is no gas over here. So it is basically inducting some gas. So when it inducts some gas, the turning moment in this diagram, in this crank, which is a function of this angle theta, this turning moment is negative. Okay, that means it is not the piston which is driving the crank. The turning moment being negative over here implies that it is not the piston which is driving the crank. Instead, the crank is driving the piston. Okay, the turning moment negative in a diagram implies that the crank is basically turning the piston. So when the crank is moving the piston, so we have to apply some externally apply some torque over on this crank. So that externally applied torque has to come from somewhere. So as to drive this piston. Okay, but so this is the required torque which has to be supplied to the system. Okay, for the motion. And when the power stroke is produced, during the power stroke only, when the gas pressure, here the combustion takes place, it is only during the power stroke that the piston drives the crank, and that torque increases by a drastic amount. Okay, so the torque increases by a drastic amount. So all of this extra torque or extra energy which is supplied to the system at a certain instant of time, let's say for this stroke, the power stroke, all of this sudden change in energy is basically stored in the system, which can be later utilized to provide these torques. Okay, so the idea is simple. So initially we need some external torque supplied to the system. Okay, so for that supplied torque in the next steps, so this is our, let's say, 4-stroke over. Then after that again 4-stroke will repeat. So the initial these two strokes we need torque that has to be supplied to this system, this mechanism, right? So that torque has to come from this torque only. So this whatever energy that we have gained in the system from this power stroke, we will store it somewhere. we will store it somewhere, and then when these strokes are required, like when the system will require energy, that device will provide some energy to the system. Okay, so that device is basically our flywheel. So what happens is that there is some energy required. This is the energy required by the system, and this is the energy produced by the system. Okay, this part is the energy produced by the system. These are the energies that has to be supplied to the system, or energy required by the system. So where from these energies are coming? These energies are basically coming from an external device which will be connected like this. So if this is a engine mechanism, so a shaft will be connected like this. A shaft will be connected like this, and there will be a device over here. Okay, so a shaft will be connected like this, and a device will be over here. Okay, so when there is some extra amount of energy that the system is producing, this energy will be passed through the shaft to this mechanical device. So this mechanical device can store energy when there is some extra energy in the system, and when the system requires some energy, this mechanical device will give up some of the energy to the system. Okay, so as to drive the piston and the other components. So basically flywheel is a device, is a mechanical device which can store energy. Okay, so what is a flywheel? So flywheel is a mechanical device which can store energy. So it is basically a energy storing device. It is basically an energy storing device. So a flywheel is a device which can store energy, energy in the form of mechanical energy. Okay, so this is a device which can store mechanical energy. Why do we need that? Why do we need to store mechanical energy? Because when the piston produces powered stroke, suddenly the angular speed of this shaft or this crankshaft will change drastically, as you can see over here. Because of this extra amount of torque, so if the turning moment over here increases, basically, so as we know from Euler's equations, that the moment is equals to I times of alpha, right? We know this, right? So if we apply some torque over here in this crankshaft, so it can rotate over this with respect to this point, right? So if the torque increases, the angular acceleration also increases, right? So if we apply a more amount of torque in this crankshaft or in this crank, so a more amount of angular acceleration will be there. So this turning moment will increase its angular velocity, basically. So if we apply a turning moment over here, a large amount of turning moment in this crank, so this will increase its angular velocity. Right, so if the angular velocity increases, so that angular velocity increase will be very high when the power stroke happens or the power stroke takes place. The angular velocity will be very high. So when a machine is operating, like an engine or something device is operating, so these kind of changes are basically undesirable. Okay, so this kind of changes in angular velocity, a sudden change in angular velocity is basically undesirable. Okay, so we generally want our angular velocity to limit to a certain extent. So a flywheel is a device which can store energy and which has a very high inertia. So what happens is that when this high amount of energy is supplied, this energy is transferred to the flywheel, and the flywheel stores this energy, and what it does is that it limits the angular velocity of this crank. Okay, so the flywheel is a mechanical device which can limit the angular velocity of rotating components. Okay, so a flywheel is a device which is connected to this shaft. So when there is no power stroke, the flywheel is a device which can supply energy to this crank in the form of rotational kinetic energy. The flywheel will give some energy to that. Okay, and it will maintain the speed of the angular speed of the crankshaft. It will maintain that. The flywheel will keep on supplying some energy. Okay, we have derived these things in the earlier lectures, like what is the turning moment in the crankshaft. So the flywheel has to continuously supply some turning moment to the crankshaft so that it can move this piston. Otherwise, this piston is providing a resisting force, right? This piston is providing a resisting force like this, right? Throughout this connecting rod, the piston is providing a resisting force like this. So there has to be some turning moment applied to this crankshaft so that this piston can move with a desired velocity, right? And this crank can move with a desired angular velocity. That turning moment is basically taken from the flywheel in the form of energy. Okay, so the flywheel is supplying some energy which is acted over here as in the form of turning moment. Okay, so energy is nothing but integral T d theta. Right, so the flywheel is basically applying some energy which is acted on this crank in the form of a turning moment, which is required to move this crank at a move this crank at a constant angular velocity. So the flywheel is continuously supplying some energy till the power stroke happens over here. Okay, so once the power stroke happens, so that power stroke is very large, so very high amount of energy is involved in this system. So this high amount of energy is taken to the flywheel. Okay, through this shaft, this flywheel takes up that high amount of energy and restricts the very high change in angular velocity of this. Okay, so there is a very high change when the power stroke takes place. There is a very high change in angular velocity of that crank. So when the flywheel is connected, this high angular velocity is restricted and flywheel takes up the energy and stores in it. Okay, once the completion of after the completion of the power stroke, the flywheel supplies the energy back to the system. Okay, so flywheel is basically an energy storing device. Why do we need to use a flywheel? It can limit the angular velocity of rotating components to a certain extent. Okay, it can limit the angular velocity of this crank to a certain extent. How does it do it? So it is basically a circular disc of very high inertia. Okay, so flywheel is nothing but, if there is a shaft, a flywheel is nothing but a disc. There will be a disc like this, circular disc. It's basically a circular disc, a very heavy circular disc. Okay, so it has a very high moment of inertia. As you can see this from this equation, it has a very high moment of inertia. So if it has a high moment of inertia, a high amount of torque is required to rotate it. Okay, it's basically like Euler's law, similar to Newton's laws. A very heavy mass requires a very high force, right? If we have a very heavy mass, we need a very high amount of force to move it. Similarly, if the moment of inertia of the flywheel is very high, to rotate it, we need a large amount of torque. Okay, so to rotate, we need a large amount of torque. Okay, so what happens is that it limits the angular acceleration. So if the angular acceleration is limited, the angular velocity will also be limited. Okay, so if this inertia is very high, the angular acceleration, as you can see from this, the angular acceleration will be limited. Okay, so for the same amount of torque, a high moment of inertia causes the angular acceleration to be less and the angular velocity to be limited. Okay, so this is the idea. So a flywheel is nothing but basically a circular disc type of device. So if a very high amount of energy is supplied to this, the flywheel will increase its kinetic energy. Okay, absorbs energy by flywheel absorbs energy by increasing angular velocity. Okay, similarly it can deliver energy by decreasing angular velocity. Okay, it can deliver some energy by decreasing its angular velocity. Okay, so what we can see is that if a high amount of torque is supplied, okay, the angular acceleration will be very high, but we can limit the angular acceleration to a low level by increasing the inertia of the system. So if the inertia of the system is high, very high, so the angular acceleration will be low. So if the angular acceleration is low, then we know that alpha is equals to d omega by dt. Okay, if alpha is very low, so from this we can find out what is the angular velocity before and after. Okay, so what are the things that we have learned about flywheel? A flywheel is an energy storage device. Okay, so it can why is it used? It is used to limit the angular velocity of the rotating components. Okay, we know that if the angular velocity is, let's say, omega 1, after the power stroke, we know that angular velocity can be at max some percentage of omega 1, not very high. So this is the meaning of this, limiting the angular velocity. Okay, so it is basically a circular disc of very high inertia. Okay, so how does it store the energy? Once the energy is supplied to the system, the flywheel will increase its kinetic energy in the form of rotational kinetic energy. So it will the flywheel will increase its angular velocity. So and it will store the energy. Okay, and when the system requires some energy, the flywheel will deliver the energy in the form of a decrement in its angular velocity. Okay, so let's do an analysis of a flywheel. So So these are the few important points about flywheels that we have learned. So let's consider that we have a shaft like this. Okay, we have a shaft like this. This shaft is connected to the engine mechanism. This part of the shaft is connected to the engine mechanism. So we have a disc. So this is a flywheel disc. Okay, this is the flywheel disc, and this is the part which is connected to the output. Okay, so this is the part. So this is a disc like this. Basically, this is the shaft and this is the disc. Okay, so the shaft and disc will be rotating like this. Okay, like this. So this is the disc. So let's say this point is connected to the engine. So if this point is connected to the engine, so we have an input torque like this, Ti. So the input torque can be a function of the angular position of this flywheel and the angular velocity of the flywheel also. The input torque can be a function of both theta and theta dot. Okay, and here let's say the input torque is something like this. Input torque is something like this. Okay. Okay, so let's say there is another output torque. So another, we will connect this part to some other part of the system. Let's say if it is an engine mechanism, we will connect these to gears and wheels furthermore. Okay, this will be connected to wheels from the engine. Okay, so there is some output torque also, let's say. So there is some resisting or output torque. So this is, let's say, the output torque, which is also a function of theta comma theta dot. Okay, so now we know from the Euler's laws. So we know from Euler's second law, right? We have learned about Euler's second law in engineering mechanics. We have learned about Euler's second law in engineering mechanics as net sum of all external moments is equals to moment of inertia about center of mass times angular acceleration, right? We have learned about that. So net moment, what are the net moment about this center of, if we look from this side, so the flywheel will be like this, and this is the shaft, this is the flywheel shaft. Okay, so this is our resisting torque, this is our resisting torque. Okay, let's say this is our resisting torque. So the net moment acting on the shaft is, this is the Ti in this direction, let's say Ti in this direction, the input torque, okay, minus the output torque. Okay, this should be equal to Ig times of theta double dot. Okay, so this is our basically the equation of motion. So this is the one of the most important equation in flywheel analysis. So this is our one of the most important equation. This I is nothing but the moment of inertia about the center of mass of this flywheel. Okay, so Ig is nothing but the moment of inertia about the center of mass of the flywheel. Okay, so this is one of the most important equation in the flywheel analysis. Okay, so this is one of our most important equation for flywheel analysis. Okay, so now you see, if the engine torque is known or the input torque is known, if we have a slider crank mechanism, then we know the input torque, right? The turning moment as a function of theta. So if this input torque and the required output torque or the load torque, if these two torques are known as a function of the angular position, we can supply it over here, we can put it over here, and we can see that this is a differential equation on theta double dot. If these two torques are known as a function of theta, then we can put it over here and we can see that this is the differential equation on the angular position. From this we can find out the angular velocity of the flywheel, angular acceleration of the flywheel at any instant of time, right? By putting these two equations over here, if these two equations are known, we will put it over here and we can solve the differential equation. Maybe analytically or numerically, that's a different thing, but we can solve to get the angular velocity and acceleration and angular position at any instant of time. Okay, so this is our basic equation of motion for the flywheel. This equation we will use frequently. Okay, so this is our basic equation of motion. We have derived it from Euler's law. Okay, so now let's understand what is happening. Okay, so this equation is generally, this differential equation is not required to solve. Why? Because we are not interested at any instant what is the velocity of the flywheel. We are not interested, in general we are not interested in such kind of questions. Our questions are different. Like our questions are, what should be the mass of this flywheel? What should be the mass of this flywheel so that it can perform satisfactorily? Okay, what should be the size or the dimension, that means basically the diameter of this flywheel, so that it can perform satisfactorily. Okay, what can be the what size or mass of the disc if we use, how much will it limit the angular velocity, how much will the angular velocity be limited? These are the few types of questions that we will try to answer in this session. Okay, so what are the basic types of problem that we can encounter is how the flywheel affects the performance. We are interested in the performance and not on the position, like instantaneous position or velocity. We are not interested in that. Basically we are interested in how does the mass of the flywheel affect the performance, how does the diameter of the flywheel affect the performance, and if we choose a certain mass and the diameter of a flywheel, how does this affect the angular velocity of the system. These are few types of questions that we will try to answer. Okay, so this is one of the equations that we will use frequently, but the differential equation we will not be required to solve in general. We will be required to solve on an average what is the angular velocity. These type of questions we will answer. Okay, let's try to understand now what happens. How does the performance of the system is affected by a flywheel? Let's try to understand. So let's say if we have a flywheel, and let's say this is the turning moment diagram that we are drawing. We are drawing a turning moment diagram. Okay, T as a function of theta. Okay, so let's say initially from 0 to some theta 1, there is no external turning moment applied. Okay, after that, let's say we are applying a constant turning moment. Up to theta 2. Okay, so this is the input turning. Since this turning moment is positive, that means energy has been supplied to the flywheel or the system. Okay, basically a type of power stroke in the system. Okay, so that means some extra energy has been supplied to the system. Okay, let's say we draw the angular velocity time diagram also. This is theta 1, this is theta 2. Okay, so this is theta 1, this is theta 2. As you can see that when the turning moment was 0, when the turning moment from this equation, Ti minus To is equals to I alpha, right? I theta double dot. When there is no input or there is no turning moment, that means angular acceleration is 0 from this equation. There is no torque, right? There is no torque. Angular acceleration is 0. This implies that angular velocity will be constant, right? From this equation, angular acceleration is 0. This implies that angular velocity will be constant. So if the angular velocity is constant, let's say from this region to this region, from 0 to theta 1, let's say angular velocity is omega 1. Okay, the angular velocity is, let's say, omega 1. Okay, once we have applied a constant torque, as you can see that there is a constant torque, right? So this delta T is some constant. This is equals to I theta double dot, right? So from this we can see that angular acceleration is also constant. From this equation we can see angular acceleration is also constant. So angular acceleration is constant. This implies that omega theta curve will be a straight line with a constant slope. Okay, will be a straight line with a constant slope. And since this torque is positive, so this angular acceleration will be positive, and it will have a positive slope like this. Okay, it will have a positive slope like this. Let's say from theta 2 to theta 3 again, there is zero torque. So if there is zero torque, so again this will be zero, this will be constant. So this is, let's say, omega 1, this is, let's say, omega 2. Okay, so here also omega 2 will remain. Now let's say from theta 3 to theta 4, or the completion of the cycle, let's say if we consider the completion of the cycle, let's say our torque has been changed, and let's say we consider this as a linear type of equation. Okay, let's say the torque variation as a function of theta is linear, like this, in this portion. So what will happen is that if the torque variation is linear over here as a linear function of theta, so if we integrate once, we will get a parabolic curve, right? So we will get a parabolic curve, and since the torque is negative, that means negative torque, so this angular velocity has to decrease, right? So the angular velocity will decrease. Angular velocity will decrease something like this. Okay, the angular velocity will decrease, and this has to be a second order curve, right? Since the torque is linear, so the torque is linear, the angular velocity will be a t is a linear function of theta, right? Over here, this is a linear function of theta, right? A theta plus b I theta double dot. So if we integrate, so here there will be a second order curve, right? So this is a second order curve. So this is a parabolic type of curve. Okay, so the angular velocity will be a parabolic type of curve. Okay, so now depending on whether this total energy and this total energy, okay, so for this point we are talking about, so this is omega 2 or omega 3, omega 2 is equals to omega 3. Okay, so the energy under this torque diagram, this area under this curve, energy E1 is area under this curve, right, which is integral t d theta, right? The area under this curve, integral t d theta, this energy E1 and this energy E2. Okay, so if these two energies, this area under this curve also, again this triangular area, this E2, this is also again integral t d theta from here to here. Okay, theta will be from theta, this will be theta 1 to theta 2, and this will be theta 3 to theta 4, t d theta. Okay, so if this E1 and E2 are equal, if this E1 and E2, that is the area under this curve and this curve, if these two are equal, that means no net resultant or external torque has, after the completion of one cycle, there is no extra amount of energy supplied to the system. Okay, if this E1 and E2 are equal at the end of this cycle, if this E1 and E2 are equal at the end of this cycle, that means there is no external energy that has been supplied to the system, right? So in that case, omega 4, this omega 4 and omega 1 will be equal. Okay, in that case, this omega 1 and omega 4 will be equal. Otherwise, if E1 is greater than E2, then omega 4 will be somewhat greater than omega 1. Or if E1 is less than E2, that means omega 4 will be less than omega 1. If E1 is greater than E2, this means that the system has absorbed some extra energy after the end of one cycle, right? So this has to be more than this in angular velocity, right? This has to be more than this angular velocity. Okay, and if we write the statements, if E1 greater than E2, this implies omega 4 greater than omega 1. E1 equals to E2 implies omega 4 equals to omega 1. And E1 less than E2 implies omega 4 less than omega 1. Okay, so as you can see that if we are supplying some energy to the system, the net energy to some energy supplied to the system, the flywheel is increasing its angular velocity. Okay, if some energy is taken away from the system, the flywheel is decreasing its angular velocity. So basically the flywheel will absorb energy or deliver energy by changing its angular velocity. This we can deduce simply from this equation. Okay, this we can simply deduce from this equation. So we can see that how the performance is affected. We are not interested in instantaneous angular velocities. Rather, we are interested in the performance of the system. And let's say after the end of theta 2, what is the angular velocity or what is the angular velocity of the flywheel? This kind of questions we will try to answer. Okay. So there is a direct relationship between the energy of the system and the angular velocities that has been changed. So we will try to find that relationship. Okay, we will try to find that relationship. So let's say during this cycle, let's say theta 1 to theta 2, during this cycle. Okay, so the initial angular velocity was omega 1, final angular velocity was omega 2. So there is something what we call as the coefficient of fluctuation of speed. This CS is called as the coefficient of fluctuation of speed. Okay, so coefficient of fluctuation of speed. Okay, this coefficient of fluctuation of speed is given as omega 2 minus omega 1 divided by omega mean. Okay, this is the omega average. Okay, this is the average omega of the system. So this average omega is given as omega 1 plus omega 2 by omega mean. Okay, this is the mean. This implies mean or average. Okay, so the average angular velocity during this stroke, as the flywheel rotates from θ1 to θ2, is the average angular velocity is this, and this CS is what we call as the coefficient of fluctuation of speed. This is called coefficient of fluctuation of speed. Okay, so this CS is what we call as the coefficient of fluctuation of speed. Okay, so this CS signifies whether how much the system's final angular velocity at the end of the stroke has been changed. From this CS we can find out how much the system's final angular velocity has been once the completion of the stroke takes place. Let's say we can find out omega 2, that is basically how much the angular velocity has changed, we can find out from this CS. Okay, from this coefficient of fluctuation of speed. So this is the definition of the coefficient of fluctuation of speed. Okay, omega 2 minus omega 1 divided by omega average. This is the coefficient of fluctuation of speed. This will signify how much the flywheel is basically limiting the angular velocity in a particular stroke, or in fact in the complete cycle. In fact, in the complete cycle also we can use this CS. Okay, how much this CS will signify how much the flywheel is limiting the angular velocity to. So see, this omega 2 is the maximum angular velocity throughout the cycle. Okay, in this case we can see this omega 2 is the maximum. In this diagram, or angular velocity versus theta diagram, we can see omega 2 is the maximum angular velocity. Okay, throughout the cycle, this is the maximum angular velocity throughout the cycle, and this is the minimum angular velocity throughout the cycle. Okay, so this is the minimum angular velocity throughout the cycle, which is omega 1, and this is the maximum angular velocity throughout the cycle, which is omega 2. Okay, so this will signify our what is the maximum limit the flywheel is limiting, how much limitation does the flywheel cause to the angular velocity. Okay, this CS will signify. Okay, okay, so now if in a turning moment diagram, if a system is supplying some energy, that means the turning moment diagram will be positive. If the turning moment diagram is positive, so there will be maximum change in the energy, right? So if the turning moment diagram is positive, then there will be some maximum change in energy in the system. Okay, so during that maximum change in energy of the system, the angular velocity change will also be maximum during that stroke. Okay, so we will be trying to relate the maximum change in energy with the coefficient of fluctuation of speed. How to do that? So we can write it like this: coefficient of fluctuation of speed equals to omega 2 minus omega 1. We multiply with this omega 2 plus omega 1 in the numerator and denominator. Okay, so we multiply with this. So this quantity is nothing but twice omega m. This quantity is nothing but twice omega m. So in the denominator we have twice omega square. Okay, and in the numerator we have omega 2 square minus omega 1 square. Okay, omega 2 square minus omega 1 square. Okay, so now after this we will multiply with the total moment of inertia of the flywheel. We will multiply with. This is the Ig. Okay, the moment of inertia of the flywheel. Okay, so here we can see now that these two will take on the numerator half Ig omega 2 square minus half Ig omega 1 square divided by omega Ig omega square. Okay, so as you can see from the numerator is that this is the maximum kinetic energy of the flywheel, right, throughout the cycle. This is the maximum kinetic energy throughout the cycle of the flywheel, and this is the minimum kinetic energy throughout the cycle, right? So this is basically nothing but the maximum change in energy. This is basically the maximum change in energy. The maximum change in energy divided by this half I omega square is the kinetic energy, average kinetic energy of the flywheel, right? Half I omega square is the average kinetic energy of the flywheel. So we can write it as twice Ek. Okay, so what do we find out? The coefficient of fluctuation of speed. The coefficient of fluctuation of speed is equals to maximum change in energy or maximum fluctuation of energy. This is called as maximum change or fluctuation in energy. Maximum change or fluctuation of energy. Okay, maximum fluctuation of energy divided by twice Ke. Okay, so this is our basic expression. Okay, so this is one of our very basic equation which we will be using frequently, very frequently. So we have this, so coefficient of fluctuation of speed is related to maximum fluctuation of energy divided by two times of the kinetic energy. Okay, so the coefficient of fluctuation of speed is related to the maximum fluctuation of energy as maximum fluctuation of energy divided by 2 times of the kinetic energy of the flywheel equals the coefficient of fluctuation of speed. So this is one of our basic equation, and the other equation of motion we have already seen. So these are the only two equations which are required to solve most of the flywheel problems that will be appearing in GATE. Okay, so we will try to solve one or two problems now. So this is a question from GATE 2013. GATE 2013. This is a question from GATE 2013. So it is given that a flywheel has to supply a energy of 400 Newton meter. So this flywheel has to supply an energy of 400 Newton meter. Okay. The angular velocity of the system is given as 20 radians per second. The angular velocity of the system is given as 20 radian per second. It is also given that the fluctuation should not exceed plus minus 2%. So the fluctuation of speed should not exceed plus minus 2%. Okay, the fluctuation of speed should not exceed plus minus 2%. Okay, we are required to find out what is the moment of inertia of the flywheel. Okay, the question is understood. If the flywheel has to supply this much amount of energy, okay, 400 Newton meter, this amount of energy has to be supplied. Okay, so the mean angular velocity of the flywheel is given as 20 radian per second. We are required to find out the moment of inertia if this flywheel has to limit this angular velocity within plus minus 2%. Okay, so this flywheel will be limiting by when it supplies this energy. Okay, this flywheel has to limit the fluctuation of this angular velocity within plus minus 2%, right? So the omega max, or according to our convention, which is omega 2, this is equals to omega plus 2% of omega, right? Omega plus 2% of omega, right? Which is nothing but 1.02 times of omega, right? This is the omega maximum. Okay, what is the omega minimum, which is omega 1 in our case? Omega minus this minus 2%, right? 2% of omega. This is equals to 0.98 omega, right? So coefficient of fluctuation of speed is omega 2 minus omega 1 divided by the average, right? So from this, omega 2 minus omega 1 divided by omega 1.02 minus 0.98. So we get basically this is equals to 0.04. So we get the coefficient of fluctuation of speed as 0.04. Now we can equate it to the change in kinetic energy, right? Change in total energy of the system from this. So we get maximum fluctuation of energy divided by twice K. So this is equals to 0.04. Maximum fluctuation of energy will happen when the energy will fluctuate in a maximum amount when the flywheel supplies an energy of this much, right? 400 Newton meter. So 400 Newton meter, 2 times of half I omega square, right? So I is basically equals to 400 times omega is given as this 20, so this is again 400. By 0.04, that is 100 by 4, this is equals to 25 kg meter square. Okay, so this is our answer to the problem. So this is basically our answer to the problem. Okay. So let's try to solve another problem. So we have this problem from GATE. So we have this problem from GATE 2014. So GATE 2014. So the turning moment diagram of the flywheel is given in the question. So this is the turning moment diagram. So this is the turning moment diagram. This is pi by 2. This is pi. And 3 pi by 2, 2 pi. This is 2 pi. And from pi by 2 to pi we have. Okay, so this is the turning moment diagram. This point is 3000 Newton meter and this is in radians. Okay, units are given as radians and Newton meter. And this is minus 1500. This is minus 1500. So this is the turning moment diagram that is given in the question. We have also the angular velocity diagram also is given. The angular velocity diagram is also given in the question. Angular velocity as a function of theta. So 0 to pi by 2, this is like this. So this is basically a 4-stroke engine which is given. A 4-stroke engine is given. Okay, so the power stroke is this much and this is the load stroke. Okay, in these two strokes basically the flywheel is supplying energy. So we have this. So this is 10 radian per second and this is given as 20 radian per second. Okay, so we are required to find out the moment of inertia of the system. Okay, moment of inertia of the flywheel. So we are required to find out the moment of inertia of the flywheel. Okay, so the question is to find out the moment of inertia of the flywheel. This is required. So we will try to solve it by two methods so that you can get an idea. So the first method, by using first method we will use the ideas that we have done right now. So what is the maximum fluctuation of energy? Let's say if we consider before this power stroke takes place, the energy of the system is E1. Before this power stroke takes place, the energy of the system is E1. After the completion of the power stroke, what is the energy of the system? E at theta equals to pi. What is the energy of the system? E1 plus this quantity is how much? This quantity area under this curve, it is 3000 multiplied with pi by 2, right? So this is 3000 area under this curve. The energy is integral T d theta, the area under this curve, 3000 vertical height multiplied with this pi by 2, right? So this is basically E1 plus 1500 pi. So this is the energy of the system at the end of this stroke. Fine. Now after this stroke, what this is the resisting torque, right? The load torque. So this will take away some energy. So at the end of the 2 pi, at the end of the complete cycle, we have energy as this one was before, this one was at the beginning of the cycle, minus now the load part, right? This load part is 1500 into 2 pi minus pi, right? So this is pi, this is 2 pi. So 2 pi minus pi is this length multiplied with this 1500, right? So 1500 pi again. This area is 1500 pi again, right? 1500 multiplied with pi. So 1500 pi. So basically what we see is that at the end of the completion of this cycle, so the total energy of the system is the same, right? As the beginning, right? So that means this point will also be of 10 radian per second. Right? This point will also be 10 radian per second. Also, we further observe that as here the turning moment is 0, so the angular velocity is constant. Here the turning moment is constant, so angular velocity is linear. Here also turning moment is constant, angular velocity is linear, right? So if the angular velocity is linear over here, okay. So now how do we relate the moment of inertia with the energy? As we know, coefficient of fluctuation of speed, right? This is equals to maximum fluctuation in the cycle, right? This is the maximum fluctuation of energy throughout the cycle. What is the maximum fluctuation of energy throughout the cycle? It is 1500 pi. As you can see, this 1500 pi is the extra amount of energy, right? This is the extra amount of energy that is supplied to the flywheel, right, or the system. This is the extra amount of the, so the maximum fluctuation is 1500 pi when the angular velocity is maximum. Okay, at the end of this power stroke, the angular velocity is maximum, right? So this is the maximum angular velocity. Okay, and at the beginning of the power stroke, the energy was E1, right? So the maximum fluctuation of energy is 1500 pi divided by 2 times of Ek. So we have to find this CS first. First. Okay, so from this, why did we do these things? This energy balance, this energy equation, this is because we were required to find out what is the maximum fluctuation of energy throughout the cycle. So we have found out that the maximum fluctuation of energy is this. Fluctuation means variation. So we have an energy E1 of the system. So it varied maximum to a maximum of 1500 pi. E1 is the energy of the system, okay, running energy of the system. So it varied to a maximum of 1500 pi at the end of the power stroke. Okay, so this maximum fluctuation of energy will be required in the coefficient of fluctuation of speed. Okay. So what do we know is that maximum fluctuation of energy is 1500 pi. So before that we need this CS. So the CS is omega maximum minus omega minimum divided by average, right? Omega maximum is 20 radian per second. Omega minimum is 10 radian per second, and omega average is 20 plus 10 by 2, right? So we have, this is numerator is 10, 30 by 2 means 15. Okay, so this is 2 by 3. Okay, so this is the coefficient of fluctuation of speed. So we have got the coefficient of fluctuation of speed from the diagram. So once we have got the coefficient of fluctuation of speed, we can substitute it over here, right? So coefficient of fluctuation of speed 2 by 3 is equals to maximum fluctuation of energy divided by I omega square, right? I times of omega square is omega square. So from this we can find out I. $15, 100, 3 5s are 5 to 10. So this is 100 pi by 10, so that is 10 pi. Okay, so 10 pi is the moment of inertia of the system. Okay, so this is by method 1. We will also try to use another method. And see how to solve the same problem. Okay, which is the next method is based on basic engineering mechanics principles, and which will be much more easier if you understand the concept. Okay. So let's try to solve it using the second method. Okay, so let's try to solve it using the next method. So the turning moment diagram was given like this. Turning moment diagram is given like this. T. So we have constant, then we have this. So this is pi by 2, this is pi, and this is 2 pi. So this is minus 1500 and this is 3000. Okay, so we can see that if we apply the Euler's law or the equation of motion of the flywheel, okay, so there is no load. So this during this power stroke there is no load, right? There is no load. So we have the basic equation of motion as T input minus T output is equals to I alpha, right? This is the basic equation of motion of the flywheel, right? So the output torque is 0 in this case. Only the input torque is there. So if the input torque is given as for this power stroke, this is constant, right? Which is 3000. So we will use this as 3000. Okay, moment of inertia is required. Now the angular velocity, right? What about the angular velocity? Sorry, the angular acceleration. We don't know the angular acceleration, right? Okay. So, but we know that if the torque is constant, that means angular velocity is linear, right? So the torque is constant. This implies that angular acceleration will also be constant. Okay. Angular acceleration will also be constant. We know that this angular acceleration has to be constant. Fine. Now from kinematic equations, we know that if the angular acceleration is constant, okay, if the angular acceleration is constant, then we have these kinematic relations, right? Omega square minus omega naught square is equals to twice alpha delta theta. Right? We know this equation, right? Similar to v square minus u square equal to twice as. Okay? We know this equation, right? If this equation is valid only when angular acceleration is constant, right? Here we have constant acceleration. We have constant angular acceleration. So we can use this omega square minus omega naught square equals to twice alpha delta theta. Delta theta is known as pi by 2 in this stroke. Okay, omega square and omega naught square are known from the graph. So we know that alpha is equals to omega 2 square minus omega 1 square divided by twice delta theta, right? This alpha we will substitute it over here. So from this we get 3000 equals to I times of omega 2 square is nothing but 20 square minus 10 square. 2 times of delta theta is pi by 2. Okay. Okay. So we can simply solve this equation. As you can see, this is 300, 3000. So I is equals to 10 pi. So as you can see, if we use basic kinematics, so as we can see, if we use basic kinematics, so we can solve this problem in one step only, okay? Whereas using the basic coefficient of fluctuation of speed, that equation, we needed 2-3 steps we needed. But if we use kinematics for such kind of problems, you see the problem becomes very simple. In one step only we can solve this same problem. Okay, so if we understand the kinematics and this turning moment diagram, solution of flywheel problems are very easy. Okay, so we will try to solve another problem where we have variable turning moment diagram given. Okay, so we will try to solve another problem where the turning moment diagrams and the loads are variables. So this is another problem. Okay, so this is another problem. So we have the input torque. This input torque is given as 800 plus 180 sine 3 theta Newton meter. Okay, so this is the input torque. So the input torque is given as 800 plus 180 sine 3 theta. This is the input torque. So the output torque or the load torque is given as 800 plus 80 sine theta Newton meter. Okay, so the input torque is given a variable and the output torque is also given a variable. Okay, so the mean angular velocity is given as 400 rpm. This is given as 400 rpm. So the mass of the flywheel is given as 350 kg. Radius of gyration, this k is the radius of gyration. So this radius of gyration is given as 220 mm. Okay, so we are required to find out what is the coefficient of fluctuation of speed. Okay, so in this question we are required to find out what is the coefficient of fluctuation of speed. Okay, so here we have to understand we don't have any further information regarding anything else. Okay, we don't have any further information. So if we want to find out the coefficient of fluctuation of speed, we need the maximum and the minimum angular velocities, right? We need the maximum and the minimum angular velocities. So if using the input and the output torque we substitute on the equation of motion, we will get a nonlinear differential equation, as you can see, because of this sine theta, right? We can get a nonlinear differential equation which is very difficult to solve. So instead what we do is that we try to draw the graphs of the input and the output torques. Let's see. So as we can see that this 800 is the mean, 800 will be mean. From these equations we can see 180 is the amplitude for the input and 80 is the amplitude for the output. Period of this input is 2 pi by 3 and period of this is 2 pi. So we can see that t is a function of theta. So the mean is 800, so we take the mean as 800. So this is our 800, let's say. Okay, let's consider this as mean as 800. Okay, so this mean is 800. So 180 sine theta 3 theta, so we have this is, let's say, pi by 2, this is pi, this is 3 pi by 2 and this is 2 pi. So this is for a single for a two-stroke engine. Okay, so this is for a two-stroke engine, so we need only up to pi. So this is, let's say, this we consider this as pi by 2. We consider only up to this. Okay, only up to pi. Okay, so how will this graph look like? So it will have 3 peaks. So 2 pi by 3, that means 2 pi by 3. -360 by 3, 120 degrees. Okay. So this graph will be something like this. Output torque graph will be 80 sine theta, right? So 80 sine theta will be something like okay. So this is our, this distance is our 80. Okay, so this is the graph of 80 sine theta, right? This is the graph of 80 sine theta. Now we have 180 sine 3 theta. So 180 sine 3 theta will be something like this. So this will be pi by 6. This will be pi by 3. This will be pi by 2. This will be pi by 2, pi by 3, pi by 2, 2 pi by 3. So this is 2 pi by 3. This quantity will be 150 degree, right? 360. Okay, so this is the graph. So as we can see that so this is basically 150 degree. So as we can see that there are two intersections between these two curves over here and over here, right? So this is the input torque. This curve is the input torque. This curve is the input torque. As you can see that this curve is the input torque. This is the input torque. Okay, this is the input torque and this is the our output torque. Okay, so as we can see that this input torque and output torque are intersecting at certain points, right? Intersecting at certain points. These points are unknown. These points are unknown. These points are we do not know at this moment. We do not know these 2 points. So as we can see that the maximum fluctuation of energy will lie between these 2 points. The energy fluctuation is maximum. The area between these two curves. The area between these two curves is maximum, right? So as we can see from this graph, the area between these two curves will be the maximum. So in this case only the energy fluctuation will also be maximum. So we are required to find out first what are these 2 points. This is our first task. What are these 2 angles where these 2 curves are intersecting? Basically this implies that the load torque and the supplied torque are equal over here and over here. Also at these 2 end points, right? The load torques are equal. The load torques are also equal at the endpoints. So we are required to find out what are these 2 angles. So how to find out these 2 angles? We simply equate these two. We simply equate these two to find out what are these two points, right? We can equate these two torques. T input is equals to T output. So what we have? So we have 180 sine 3 theta minus 80 sine theta should be equal to 0. Fine. 9 sine 3 theta we can write it as 3 sine theta minus 4 sine cube theta. Minus 4 sine theta should be equal to 0. Okay. So now we can solve. So this equation can be solved as, this equation can be written as 4 9s are 36, 3 9s are 27 minus 4 is 23 sine theta minus 36 sine cube theta. This should be equal to 0. Okay. So now this is a cubic equation which we can solve. We can simply solve this cubic equation. So how do we solve this cubic equation? We take sine theta as common. We take sine theta as common and we can write it as 36, or rather write 6 sine theta whole square minus root over of 23 whole square. This should be equal to 0, right? This should be equal to 0. So from this we can see that either sine theta should be equal to 0, sine theta should be equal to 0, or this equation 6 sine square theta, 36 sine square theta should be equal to 23. Fine. 36 sine square theta should be equal to 23. So these are the two solutions possible. So if, but this quantity will give us theta equals to 0 comma pi, right? This thing will give us 0 comma pi. This is not desiredable. This shows the end point of the cycles, at the beginning and the end of the cycle. So this is not desirable. We want the midpoints, right? So from this we can see that sin theta will be equal to plus minus root over of 23 by 6, right? Plus minus root over of 23 by 6. Also from 0 to pi sin theta is not negative, right? So this mathematically this is plus minus, but we know from the graph that sin theta is non-negative, right? From 0 to pi sin theta is non-negative. So we only need the solution for sin theta equals to positive of root over of 23 by 6. We only need the solution to this. Okay, so we can take a sine inverse to find out the solution to this. So the solution to this is theta is equals to 53 degrees. Okay, so the solution to this is theta equals to 53.03 degrees and 126. You can take a sine inverse to find it out from calculators. Okay, 126.97 degrees. Okay, so within these two angles, our fluctuation of energy is maximum. Okay, so our fluctuation of energy is maximum within these two angles. Okay, so how do we find out the maximum fluctuation of energy? So maximum fluctuation of energy can be found out like this. So maximum fluctuation of energy delta E, maximum fluctuation of energy is delta E. Integral limits will be from 53.03 to 126.97. Okay, and delta T, right? T input minus T output, delta T. So delta T is 180 sine 3 theta minus 80 sine theta. Integral delta T d theta. Okay, this is the maximum fluctuation of energy. Integral delta T d theta, this is the maximum fluctuation of energy. Okay. So now we can integrate this equation. After integrating this equation, once we integrate this equation, we will find this out, the solution. After integration, the final answer of this is minus 208.3 Newton meter. Okay, this minus was evident because the load torque was greater, right? The output torque, the graph was something like this. Okay, and the mean line was this, right? So this torque was evident, right? This quantity is less, right? So this minus was evident. So this implies that energy has been taken from the flywheel, right? This implies that energy has been taken. How this minus was evident? Because it is below the mean line, right? This was the mean line, right? 800 was the mean line. So this curve was more. The area under this curve was more as compared to this, right? So the minus was evident. Okay. So this minus implies that the flywheel has given some energy to the system. Okay. The flywheel has given some energy to the system. Fine. So now we can relate the coefficient of fluctuation of speed, right? The coefficient of fluctuation of speed, maximum fluctuation of energy by twice kinetic energy. Okay, rest other things are given. So while using this, we will not use we need only the magnitude. We only need the magnitude. So we will substitute this 208.3 divided by I omega square. I is nothing but mk square. Okay, I is nothing but mk square. Radius of gyration is given. So I is mk square. Mass is given. Radius of gyration is given mk square. Omega will be substituted in terms of radians per second. Fine. So we will get the coefficient of fluctuation of speed as 0.7%. Okay, so this is the answer to the problem. This is the answer to the problem. Okay. So with this our basics of flywheel is almost over. Okay, we will try to start off with gyroscopes now. So please try to solve more problems in flywheels, and if you find any difficulties, then please feel free to text me on WhatsApp. So we will continue with the concept of gyroscope and gyroscopic effects. So let's understand what do we mean by a gyroscopic effect. So gyroscopic effect. So what happens is that let's consider a coordinate system like this. So this is a 3D coordinate system. So let's consider a 3D coordinate system like this. This is x, this is our y, and this is our z axis. So if we consider a 3D coordinate system, so let's say we have a rotor like this. So we have a disc which is rotating about this axis. Okay, so this is the angular velocity. So we have a rotor like this. So we have a rotor like this which is rotating about like this with an angular velocity omega, let's say. So this is the rotation according to the right hand rule. So this is our x-axis. So this is the angle of rotation. So if we look from this side, so from this side it will look at if we look into the disc like this, so it is rotating like this in the counterclockwise direction from this side. Okay, so the angular velocity vector has a direction like this. Okay, right hand thumb rule. The angular velocity vector has a direction like this. So like this. So according to the right hand thumb rule. So omega vector is given as magnitude times Ex. Okay. So Ex is the unit vector along the x direction. Ex is the unit vector along the x direction. Okay. So now if this rotor while rotating, so this angular velocity is called as the spin angular velocity. Spin angular velocity. Okay, so this angular velocity is called as the spin angular velocity. Okay, so now if this rotor while spinning about its axis, okay, is also given a rotation, is also given a turn in any other direction, okay, in any of the other direction. Let's say if we consider the xy plane, like this, if this is the xy plane, so the angular velocity vector is like this, which is rotating like this. Okay, the disc is rotating like this, angular velocity. Now this angular velocity vector is given a turn in this plane, in the xy plane, like this or like this, either in this direction or in this direction. Okay, if this angular velocity vector, this is the angular velocity vector, the axis of spin, if this axis of spin is given a turn in this direction or in this direction or in any other direction, then there will be a resisting effect. This resisting effect is what we call as the gyroscopic effect. Okay, so what do we understand by gyroscopic effect? If a rotating body, if a spinning body about its axis is given a turn about, if the spinning axis is given a turn about any other arbitrary axis, then there will be a resistance to this turn. Okay, then there will be a resistance to this turn. We will not be able to freely rotate this. Okay, the spinning axis, we will not be able to freely turn this spinning axis. We have to apply some external torque to rotate this spinning axis. Okay, so if we want to rotate this spinning axis or turn this spinning axis, there has to be applied some external torque. Okay, so the phenomena which is resisting this external torque is what we call as the gyroscopic effect. Okay, so this is basically a sort of inertia type of system, right? Like what is inertia? If the inertia is a property by which we have to apply a force to move a object, right? So basically inertia is opposing the force, right? It is a resisting force which is opposing the externally applied force. It's the similar like Newton's law, right? Like Newton's law. So if we have F equal to ma, so this mass is the inertia, right? So this is the inertia, right? So this inertia is basically resisting the external force, right? Similarly, gyroscopic effect is the effect which is resisting this turning of the spinning axis. The effect which is resisting the turning of the spinning axis is what we call as the gyroscopic effect. Okay. So this is what we mean by gyroscopic effect. So this kind of phenomena is very important in aeroplanes, then in naval ships, where then also in automobiles where the wheels are rotating and the automobile is taking some turn or something like that. Okay, similarly in aeroplanes we have the propeller, right? We have the wing, like if we consider this as the aeroplane, there will be a wing like this and there will be a rotating disc like this, right? Aeroplane or something. So this is the wing, this is the aeroplane. So there will be at the front of the aeroplane, frontal nose, there is a rotating rotating fan or rotating propeller like this. Okay, so this rotating propeller also, this is let's say if it is rotating like this about this is the axis. If the now aeroplane has to take a turn, then this aeroplane will experience a gyroscopic effect. Okay, so these kind of effects are important for this. Fine. Okay, so we will try to find out what do we mean by the rate of change of angular velocity. Okay, this is important. So we have to find out the angular velocity. The spin angular velocity is this. The definition is very well known. We will now tend to find out what is the rate of change of this angular velocity. Okay, the rate of change of this angular velocity. So the rate of change of angular velocity is nothing but our angular acceleration. This is our nothing but angular acceleration. So what is the angular acceleration? We will try to find it out. Okay, so we will try to find out what is the angular acceleration first. Why this is required, we will see in a short moment why this is required. So d omega by dt, right? So d omega by dt is nothing but ddt of omega ex vector, right? ddt of omega ex vector. Now you see a scalar multiplied with a vector, the differentiation of a scalar multiplied with a vector, right? So we can, what do we do? So we do the product rule, d omega by dt times of ex plus omega times ddt of ex vector. Okay, so the product rule of differentiation has been used. The product rule of differentiation. So d omega by dt is nothing but our rate of change of angular velocity, which is omega dot. The direction of this is along the ex direction only. Okay, so this signifies the rate of change of magnitude of the angular velocity, right? If the angular velocity has a direction along the x direction and its magnitude is only changing, okay, that means we have an angular acceleration which is changing the magnitude of the angular velocity. This causes the change in, this is because of the change in magnitude of the angular velocity. Okay, and this quantity is, as you can see, this ddt of ex vector, this is a differentiation of the unit vector in the x direction, right? Because this spin axis is turning, right? So the differentiation of this represents the rate of change of direction of the vector, right? So we have like this omega ddt, we can write it as dg theta of ex vector times d theta by dt, right? Now what is this theta? We have to understand that. Now if we look into this disk from the top direction, right? If we look into this disk from the top direction, okay, basically the xy plane, if we look at it from the xy plane, so we will have this as the y and this is the x direction, right? This is the y and this is the x direction, right? We will have this as the horizontal as the y and vertical as the x direction. So our angular velocity vector is in this direction, right? This is our angular velocity vector. Angular velocity vector is in this direction. So if the angular velocity vector turns like this, so this is our angular velocity vector after some time. Okay, so this angle is what we call as d theta. Okay, this angle is what we call as d theta. So basically, if the angular velocity was initially from in the xy plane, if we draw the xy plane in this, so the angular velocity is like this, right? Initially, this is our origin. So the initially angular velocity of this is like this, OA. Finally, the angular velocity became this one. This is B, right? So the change in angular velocity, which is the angular acceleration, the change in angular velocity with respect to time is the angular acceleration, is nothing but has a direction like this, right? Has a direction like this. Change in angular velocity has a direction like this. This AB vector is given by the AB vector, right? Okay, so this has two components, one along this and one perpendicular to this. So along the direction of OA we have this quantity, and perpendicular to the direction of OA we have this quantity, which represents the angular velocity change because of the change in the direction of angular velocity. That means even if the magnitude of angular velocity is constant, but the spin axis is turning, we will have this quantity of angular acceleration. That means omega dot will be 0, but because of the change in direction, we will still have an angular acceleration, just like the centripetal acceleration. Okay, even if a particle moves in a curved path with a constant velocity, let's say a particle moves in a circular path, at constant linear velocity. Even if the linear velocity is constant, there is an angular acceleration, right? There is an acceleration, right? Even if the particle moves with a constant velocity v, there is an acceleration perpendicular to v, which is v square by r, the centripetal acceleration, right? A similar concept over here. Even if the angular velocity, here it was linear velocity, here we are considering angular velocity. Even if the angular velocity is constant in magnitude, okay, okay, but the change in direction produces an angular acceleration, which is this quantity, which is given by this quantity. Okay. So now we can find out what is this quantity, just as we have done in engineering mechanics. So we can write the angular acceleration vector as omega dot ex plus, we can see that if in the xy plane, let's say this is our xy plane, so this y, this is x. This is x, this is y, let's say. Okay, so this is our xy plane, let's say. Okay, from the top view, this is the top view basically. So the angular velocity is like this, right? This is the direction of ex. This is the direction of ex, and this is the direction of ey. This is the direction of ey, right? This is the direction of ey. Now, if this ex turns, let's say ex turns, consider a circle like this. Okay, now this is the magnitude of the angular velocity. Okay, now if this angular velocity, the spin axis turns like this, if the spin axis turns like this, okay, so the change in angular velocity will be like this, right? So this is a large angle, right? If we keep this angle very small, if we keep on taking this angle very small, this delta theta, if this is our delta theta, the more we keep this angle very small, then delta theta by delta t will tend to d theta by dt. Okay, so we see that if this angle is more small, we can see that angular velocity will be here. So this change is here, more small here, change is here. So under the limit, this under the limit, this will tend to the tangential direction, right? This will tend to a direction which is perpendicular or tangential to this circle, right? Or basically perpendicular to the opposite to this ey direction, right? This will be basically opposite to this ey direction. So dex by d theta is opposite to ey, right? So this is dex by d theta is basically minus ey, right? And d theta by dt we call it as omega p, let's say. Omega dex by d theta is minus ey. Okay, dex by d theta is minus ey. So we have omega dot ex minus omega p omega ey. Okay, this minus signifies that it is along this direction. Okay, this minus has nothing else. The magnitude is omega p omega, and the minus signifies that it is along the opposite to ey direction. Okay, so this is based on our coordinate system. Okay, this is based on our coordinate system. So you see, what type of coordinate system have we taken? We have taken a right-handed system. So we have taken a right-handed system. So we have taken a system like this. So this is our z-axis, this is our x-axis, this is our y-axis. Okay, so the angular velocity is in this direction initially, omega vector. Okay, so if it is turning in this direction, let's say. Okay, if it is turning in this direction, let's say something like this, turning in like this. Okay, in a horizontal circle, okay, in a horizontal circle along the xy plane, okay, in the horizontal circle along the xy plane, then the angular acceleration is given as omega dot ex vector minus, that means it is opposite to the, if this is the y axis, this is in the that direction, right, into the board. Away from the board is our positive y axis and into the board is our negative y axis. So this is minus omega p omega e y axis. Okay, so what is this omega p? What is this omega p? Omega p is nothing but, omega p has a direction nothing but like this, right? It is delta theta, right? Theta in the horizontal direction, right? So omega p is like this. Omega p is like this. So it is a rotation in the horizontal plane, and according to the right hand thumb rule, this is a rotation like this. That omega p has a direction like this along the positive z direction. Okay, along the positive z direction. So this is the magnitude of our angular acceleration. So this is a very important equation. This is a very important expression. So this is the magnitude of our total angular acceleration of the object. Okay, total angular acceleration of the object. Fine. So if we have a constant angular velocity, constant spin angular velocity, we consider this as spin. This is spin. Okay. If we have a constant spin angular velocity, and the spin angular velocity, the axis of the spin angular velocity takes a turn, then this quantity will be 0, but still there will be an angular acceleration, which is this. Okay, this angular acceleration causes what we call as the gyroscopic effect. This angular acceleration is responsible for causing the gyroscopic effect. Okay, now let's understand why we have used this. Okay, so if again we take our coordinate system like this, this is our y axis, this is our x axis, and this is our z axis. Okay, this is our z axis. Fine. Okay, so now let's say if we have a rotor like this, if we have a disc or rotor like this, okay, so this disc, okay, has an angular velocity. Okay, this disc has an angular velocity, let's say along this direction, this angular velocity. Okay, this disc has an angular velocity like this. Okay, and the disc has a moment of inertia about this axis, the axis of this disc. The moment of inertia about this axis of this disc is, let's say, Ig. About the center of mass axis of this disc is, let's say, moment of inertia is Ig. Okay, so what is the angular momentum of this disc? The angular momentum of this disc is given as Ig times of omega vector. Okay, the angular momentum is given as Ig times of omega vector. The angular momentum of this disc is given as H vector is equals to Ig times of omega vector. Okay, Ig times of omega vector. This is the angular momentum which has a direction along the x direction, right? Which has a direction along the x direction. Now, if we say that the rate of change of angular momentum is nothing but our equal to the external torque, right? Euler's law, Euler's second law. The rate of change of sum of all external moments or torques is equals to the rate of change of angular momentum, right? Okay, sum of all external moment equal to rate of change of angular momentum. We know this, right? Now we have to differentiate this. So for this, moment of inertia will remain constant. So d omega by dt we have already found out. We can substitute, right? D omega by dt we have already found out. So we can, for rate of change of angular momentum is equal to the impressed moment, right? External moment. Right, the rate of change of angular momentum is equal to the external moment, right? Is equal to the external moment, right? So from this we can find out this. So the external moment, sum of all external moments is equals to the rate of change of angular momentum, right? rate of change of angular momentum. So the rate of change of angular momentum is nothing but Ig times of omega vector. Okay, so the rate of change of, so Ig is constant, it is the moment of inertia. We can take it out. We can take it out of this Ig times of ddt of omega vector, right? So this is nothing but the angular acceleration, which is this. Angular acceleration, which is this. This we have already derived. So sum of all external moments about the center of mass is equals to what? Ig times of omega dot Ex minus omega p omega s Ey. Okay. Okay. So we have two equations over here. Moment of sum of all external moment about the x-axis and sum of all external moment about the y-axis. You see, y, we have y. So this is the vector equation. So we have two equations over here. Okay. So we have two equations over here. So we have two equations over here. What do we get? Sum of all external moments about the center of mass along the x-axis. Sum of all external moment about the center of mass along the x-axis is Ig times of omega dot I alpha, basically. Net sum of all external moment is equals to I alpha. Okay, this is basically the equation. And the second equation what we get is that net sum of all external moments, okay, along the y direction is equals to Ig omega p times of omega s. Okay, omega p times of omega s. Okay, Ig omega p times of omega s. This minus is also there, obviously. So this minus is also there. So this minus implies the direction of the moment, right? So our positive y-axis is this. So negative y-axis will be like this, right? Negative y-axis will be towards the board. So sum of all external moments is towards the board, right? Sum of all external moments is towards the board. So the minus signifies only the sum of all external moments towards the board. This implies that if we have a disc like this, rotating, which has an angular velocity like this, okay, which has an angular velocity like this. So sum of all external moments, so this is our x-axis, sum of all external moment in this direction, okay, in this direction, clockwise direction, okay. So this clockwise direction, sum of all external moments in the clockwise direction, mgy, this is equals to Ig omega p times of omega s. Okay, so this is our basically what we call as the gyroscopic torque or the gyroscopic moment. Okay, this is what we call as the gyroscopic moment. So this equation is what we call as the gyroscopic moment. Okay, and this is basically Euler's second law. This is basically the moment along this axis, the torque along this direction, basically the torque like this. Okay, this torque will create this. Okay, and the moment along this direction, this external moment, this is the cause of the gyroscopic effect. Okay, so what do we understand is that if there are two inferences from this that we can understand, there are two equations of motion that we have got, moment along the x direction and moment along the y direction. Okay, so there are two inferences that we can get. Okay, so if we apply external moment in this direction, let's say the disc is rotating like this, this is the first inference, the disc is rotating like this, okay, in the counterclockwise direction from this, like in the positive, angular velocity is in the positive direction like this. Okay, so if we apply a moment like this, okay, clockwise moment like this, if we apply a clockwise moment to the spinning disc like this, this clockwise moment will cause this disc to turn in this direction. Are you getting me? Are you getting me? So if we apply to the spinning disc, if we apply a moment in this direction, basically if we apply a moment like this, okay, moment like this, so this external moment will cause this disc to turn like this, in the along the board like this. Okay, if we cause a clockwise moment like this, it will turn the body like this. If we apply a anti-clockwise moment like this, the body will turn like this. The body will basically, if we cause a clockwise moment like this in the y direction, if we cause a clockwise moment in the y direction, the body will turn like this, okay. And if we cause an anti-clockwise moment like this, the body will turn like this, okay, in the outward from the board like this. Okay, so this is one of the inferences, okay, that if we externally apply some clockwise moment, the spinning disc will try to move in this direction. Okay, whereas if we apply anti-clockwise external moment, the spinning disc will try to move in this direction. So how to identify the direction in which the spinning disc will move? So this can be found out from a vector cross product. This equation can be written like this: Ig times of omega p vector cross omega s vector. This will give us the direction of the gyroscopic couple. Okay, how do we find out the gyroscopic couple? Omega p cross omega s. How? Omega p is in this direction and omega s is in this direction, right? So omega p cross omega s. So this is the direction of the gyroscopic couple, as you can see. Okay, so if this is applied, omega p cross omega s, so this will be the direction. This will be the direction of the external moment, which will cause this disc to turn like this. Okay, which will cause this spinning disc to turn towards the board. Okay. Similarly, if the omega p is in this direction, okay, omega p is in this direction. So we have omega p cross omega s. So omega p cross omega s, right? Omega p cross omega s, right? So we have omega p cross omega s, right? So the disc will turn like this. And we have to apply an external moment like this in the anti-clockwise direction. So what are the inferences that we have got? If we apply a clockwise moment, from this concept, we try to match with the direction of this. So our omega p has to have such a direction so that omega p cross omega s has to be equal to the external torque direction. Okay, so how this torque can be achieved? If omega p has a direction like this in the vertically upward direction, so omega p cross omega s gives a direction which is similar to this torque. That means the omega p will have a upward direction, omega p vector will have a vertically upward direction. This implies that if we apply a clockwise moment, the spinning disc will turn like this, right? Turn like this. Omega p has a vertically upward direction, the spinning disc will turn like this, okay, along the direction of omega p. This is for clockwise moment. Now let's say if we have an apply an externally anti-clockwise moment, externally applied anti-clockwise moment, let's say like this. We apply an externally applied anti-clockwise moment like this, okay, like this. So omega p has to have a direction in such a way so that it matches with this direction. Okay, so the omega p direction has to be like this. So omega p cross omega s gives a direction which is anti-clockwise like this. So if the omega p is in the downward direction, that means the disc will rotate in this direction. Okay, spinning disc. So if we apply an external moment to a spinning disc, the disc will turn in these directions or in this direction. This is one of the inference. Okay, this torque is called as the gyroscopic torque. Fine, this is one of the inference. Second inference is that if a spinning disc, if this disc is spinning, and if we try to rotate the disc turn the disc in this direction, then we will experience a resisting torque like this. Okay, the second inference is this, which is vice versa. That means earlier we have applied an external moment in the clockwise or anti-clockwise direction, which caused the turning of the disc, right? Now if we somehow try to turn the disc, we will face a resisting moment. This is the inference. That means earlier we have externally applied this, now we are externally trying to apply this. Okay, because of this gyroscopic couple, we will experience a resisting moment in the perpendicular direction. That means if we have a omega vector in this direction, omega p vector, and omega s vector is in this direction, that means if we have a spinning disk like this, and we are forcefully trying to turn this disk like this. Okay, if we are forcefully trying to turn this disk like this, we will experience a moment in the omega p cross omega in the clockwise direction like this. Are you getting me? So if there is a spinning disk like this, we are forcefully trying to turn this disk in this direction, so we will experience a moment in this direction. Okay, we will experience a moment in this direction. So this is the basically these are the two inferences for gyroscope that we can understand. We will try to solve few problems. Okay, so first problem is from GATE 2016. Okay, so how to find out for the gyroscopic disc, how to find out the direction omega p cross omega s. Okay, so this is the direction, this will give us the direction of the gyroscopic torque. Okay, so let's try to solve the first problem. This is from GATE 2016. So a car is moving on a horizontal road. Okay, a car is moving on a horizontal road. Let's say we have a car like this. A car is moving on a horizontal road like this. Okay, so this car is moving in a horizontal road like this, and it experiences a turn. And it experiences a turn like this. In a circular turn, it experiences a circular turn like this. Okay, so it experiences a circular turn like this. So the radius of this turn is given as 100 meter. So this radius is given as 100 meter. So the linear velocity of the car is given as 20 meter per second. Okay, so the wheels of the car has a mass of, the wheels of the car has a, okay, the mass is not given. So the wheels of the car are rotating at an angular velocity of this 100 radian per second, 100 radian per second clockwise. 100 radian per second clockwise if we look from this direction. If we look from this direction, 100 radian per second clockwise. From this direction, if we look 100 radian per second clockwise, moment of inertia is given as 10 kg meter square. 10 kg meter square. We are required to find out what is the net gyroscopic torque experienced. Okay, what is the net gyroscopic torque experienced by the wheels? We are required to find out. Okay, so what do we need to find out? So we see that the spin angular velocity is given. The spin angular velocity has a direction like this, right? If this is our x-axis and this is our, let's say, in the plane, so it is our y-axis, let's say, and this is our z-axis. Okay, so this is clockwise, right? So it is given as clockwise like this. From, if we look from this side, the wheels has to rotate like this, so this is clockwise. So in the minus x direction is our spin. So omega s is along the minus 100 ex. Okay, omega s vector minus 100 es. Okay, and now if it takes a turn like this, so omega p vector has, the magnitude is yet unknown. We will find it out. Omega p vector. So it is turning like this. So this is a positive direction. So it has a positive direction of ez direction. Okay. So omega p magnitude is unknown. Direction is known as known. The direction is like this. Since the car will take a turn like this, so according to the right hand thumb rule, so positive z direction is along this. So it is along the positive z direction. So this is known. So moment of inertia of the wheels are also known. The spin moment of inertia. This is also known. So how do we find out the magnitude of the precision? This is also called as angular velocity of precision. Okay, angular velocity of precision. Okay, This is called as the angular velocity of precession. Okay, so basically the spinning axis is precessing. So this is called as the angular velocity of precession. So how do we find out this omega p? To find out this omega p, we know that this linear velocity is known. This linear velocity is known. So omega is nothing but linear velocity divided by the radius of curvature. So the linear velocity is 20, radius of curvature is 100 meter. 1 by 5 radian per second. So this is our angular velocity of precession is given as 1 by 5 radian per second. So now we know both the magnitude and direction. So the gyroscopic torque is Ig omega p vector cross omega. So from this we can find out the direction also. So Ig is 10 multiplied with 1 by 5 multiplied with 100. Okay. Okay. So this is our direction. So omega p cross omega. What is the direction of omega p cross omega? Omega p is in this direction. So omega p cross omega, right? According to the right hand rule. So Ex cross Ez. From this we can find out omega p cross omega. This is equals to 200. So gyroscopic torque is equals to 200 Newton meter. And what is the direction? Direction we can find out from this, right? Omega p cross omega s. Omega p is in this direction. Omega p is in this direction. Omega p cross omega s, right? If we have to use omega p cross omega s. So this is along the minus Ey direction. So this is along the minus Ey direction. Newton meter. Okay, so as you can see, omega p cross omega s. Omega p cross omega s. So this is along the negative y direction. So minus Ey. Fine. So this is the solution to the problem. So this gives the solution to the problem. Okay. We'll try to solve another problem. So there is a universal bearing. So there is a universal bearing over here. This is a universal. Consider this is a universal bearing. There is a long rod like this, connected like this, and we have a spinning disc over here like this. We have a spinning disc over here like this. So this is our x-axis. This is our z-axis. So the spinning disc has a mass of 8 kg. So the radius of gyration is given as 150 mm. The length of this rod is 200 mm. The length of this rod is 200 mm. Spin angular velocity is given as 240 rpm. What is the precision we are required to find out, and we are required to find out the angular velocity of precession, its magnitude and direction. Okay, magnitude and direction of the angular velocity of precession. So what we see is that if we draw the free body diagram of this system, so this is the rod and this is the disc, right? So weight of the disc will be acting downward, right? Vertically downward. Okay. Now this mg will create a moment about this point, right? This is point O. So this mg times of L is the net external moment, and this is R cross F in the clockwise direction, right? So this is the clockwise direction. So externally applied moment is mg times of L. Externally applied moment is mg into L, right? Externally applied moment is mg into L, right? So mg into L is the external moment about point O. Okay, so the disc is spinning. So the disc is spinning, the direction of the spin is given as clockwise. Okay, so the direction of the spin is given as clockwise. So this omega s is given as clockwise if we are looking from this direction. Okay, if we are looking from this direction, the angular velocity direction is given as clockwise. So angular velocity direction is clockwise, that means disc is rotating like this. So disc is rotating like this. So omega s is minus, this is in this direction, right? Okay. So this is the externally applied moment in the clockwise direction. So we have this externally applied moment will create the gyroscopic effect, right? This should be equal to Ig omega p times of omega s. Okay, so what should be the precision we can find out? From this equation we can find out the magnitude of the precision as mgl divided by Ig into omega s. So from this we can find out what is the precision. So the precision comes out to be around 3.47 radian per second. Okay, after substituting all the values, we get the precision to be 3.47 radians per second. So this is the magnitude. What should be the precision? That means in which direction this disc should turn, we have to find that out. So this we can find out from the cross product omega p cross omega s. So that this cross product should have a direction consistent with this externally applied moment. So omega p cross omega s. If we take the omega p as vertically upward, then we have omega p cross omega s, right? Omega p cross, since omega s is in this direction, so omega p cross omega s. So this is not matching with this direction, this is incorrect. So we have to take omega p vertically downward. So in this case we have omega p cross omega s, right, which is along this towards the board. So this clockwise moment is also towards the board, right, which is consistent. So this implies that this disc will be turning away from the board. Okay, so the omega p will have a direction of minus Ez direction. Okay, so omega p will have a direction minus Ez direction. Okay. With this, I would like to end in today's lecture. So in the next lectures, we will start off with some cam follower systems or gear trains. Okay. So please try to practice more problems. Thank you.